Okay, so the next talk will be given by Prudence Jagpa, who last year has been a tutor here at Ames Rwanda, but is going to talk about his work that was done during his PhD at Stellenbosch.
Yes.
And it's about subgroups of Beidleman near vector spaces.
Thank you. Hello, everyone. So I'm going to be discussing on the R group of Rn, where R is a near field. Okay, so this area might be new for you. I will go slowly and define the basic concept so that we all are on the same page. Okay. So I will be following this outline. Okay, so the concept of nearing and near field starts at the beginning of 20th century by the mathematician called Beidleman. So the idea is that he takes the structure of field and ring, and we omit one of the descriptive law, and we see which structure what can be used with this new structure that we just derive. And a near ring is defined as a set, non-empty set with two binary operations, such that R is a group. Everyone know what is a group. R with multiplication is a semigroup. A semigroup is closure and associativity. And then we have only one distributive law. So here we call it as left nearing. So we could also define right nearing. So the other distributive law is omitted. Okay. So an example, a natural example of nearing is when we consider a set with additive group, and then we consider the set of mapping MJ. MJ is a set of all mapping from an additive group to this additive group is formed a near ring. It's not a ring. Why is not a ring? Because of the left distributive, the right distributive does not hold. Maybe an example, if I give you, I define a function f, a, which is defined from G to G, such that fa of x is equal to a. And I define another fb of x is equal to b, fc of x is equal to c. So if we suppose that a is different of 0, then we can compute f a composed with fb we can compute this, and we see that C, this one will give us C plus C. But we can also compute differently A composed with FB plus FB composed with FC. And this will give us, this one will give us C, and this will give us C plus C. So if I assume that C is different of 0, then this equality won't hold. So that's why this set is a near ring, which is not a ring. So when we define this new structure, we found out there are some basic rules that we all know in ring that does not hold in this new structure. For instance, we know that in ring, if we take R as a ring, we know that 0R is equal to R0 equal to 0. That is always true. But here is not true for near ring. I give you an example. If I consider a function f, which is a cosine x from this nearing that we just give an example. So if we found out that you compose f of x with this 0, it will give you cosine of 0, which is 1. So it's different of 0. But we're gonna assume that these equality hold. So every nearing where this equality hold is called zero symmetric nearing, because we require this to do our work. Now, a near field is a nearing where the multiplicative group is a group. That's all. And these are being introduced by Dixon in 1905. And later, there have been some work that have been done in that area that is related to geometry. Yeah. So if you want to represent some pair, some point and non-vertical line, we can take the pair in a certain structure X. So he proved that this structure is exactly a near field. So later, the mathematician House classify all finite near field. He found out that all finite near field are finite Dixon near field, except 7 exceptions. So I will not give you the 7 exception. But before we explain how we can construct all finite Dixon near field. And later, from the definition of a near field, the commutativity under the additive group is not trivial. But this mathematician proved that the additive group of a near field is always abelian. And another one proved the same thing in different way. Now, we know from a field theory that if you have a finite field of order p to power n, there exists a subfield which is of the order p to power k, where k divide n. So this mathematician called Susan Danks proved the same result, but in different way. There is also an application of this, the near field in cryptography. So if we want to encrypt a certain message, a plain text to receive text, we need the matrix M. Now, if you suppose that the element of that matrix is taken from a near field, then how can we compute the inverse of that matrix to recover the message? But here, the multiplication of matrix is not the same as we do. So for instance, the associativity under the multiplication law for the set of matrices does not hold all the way. So here, there are some work that have been done in that area. It's just for square matrix. Can we find the inverse of a matrix? And then that's what he did for encrypting a message using a near field. So as I say, to construct a finite near field, Dixon defined what we call a pair. A Dixon pair is 7, 9, 3, 2, and so on. So we'll be using the finite Dixon near field that arise from the Dixon pair 3, 2. So how can we do that? We know that a finite field is cyclic generated by G. So we take a subgroup of that. So first of all, we assume that Qn is a Dixon pair. It satisfies the condition that I showed before. And then we take a subgroup which is generated by Gn of Fqn. So the quotient group will be presented as this one. The quotient group will be presented as this. But now the set Q to power K minus 1, Q minus 1 form a complete set residual modulo n. That's why the quotient group can be presented as the last equality. Then we can define a new multiplication. So the idea of constructing a Dixon near field is that we start with a Galois field of order Q to power n. We conserve the addition, but now we distort the multiplication. We change the user multiplication to become a new multiplication. So how we define the new multiplication is defined as this. So that alpha belongs to a specific coset. That is the following step to derive a finite Dixon near field. An example, if I take the Dixon pair 3, 2, we know that the finite field is isomorph to the field Z3, the ring field divided by the quotient, the heredity polynomial. This one is an irreducible polynomial. So all the elements will look like this. And then we can derive the coset since we are taking the subgroup of F through 2. The subgroup is denoted by G square. That's why we require that the element A should be a square. So this is an example. And this example is a near field that is not a field. Why? Because the commutativity under the multiplication does not hold. An example for this table for the operation, we see that here, if we take this multiplied by x, we find 2 plus x. But if we take 1 plus x multiplied by x, we find 1 plus 2x. It doesn't work. Okay, so to define near vector space, we'll be defining what we call a nearing module. A nearing module is an identity group which satisfies those conditions. But here, we should know that one of the descriptives is omitted. Normally, we should have that this one, we should have the descriptive over the scalar as well. So we omit that one. That we call a nearing module. Okay? So what we call R-subgroup here is an identity group, a subgroup of nearing module which satisfy this. Like we have the closure under scalar multiplication. And we will define what we call submodule here. Since one of the distributive law is omitted now, we do not have the distributivity over the scalar. That's why we add this condition for the definition of submodule. Okay, so if you take this example of vector space, a submodule here is coincide with R subgroup. They are the same. But since we are omitting one descriptive law, we have to separate them. So an example, if every submodule is R subgroup, if we take M equal to 0, we find that it will follow. So as I was saying, one of the descriptor is omitted. So what we're going to do now is that we suppose that if we take M to be the direct sum, M1 plus M2, and then we can write every element as of M to be M1 plus M2. So we can show that this element can permute if M1 and M2 are from different submodules. This is easy to prove. And as well, if you consider that M is a direct sum of submodule, when we multiply the scalar by an element M, we can distribute the scalar over the element. So as an example, to prove this, if we consider 2, so we just have to show that M1 plus M2 R minus M1 R minus M2 R belong to the intersection M1, M2. Since M is the direct sum of M1, M2. So since M1 is a submodule and M2 is a submodule, you see that this one belongs to M2. And as well, this is in M2. So therefore, the summation is M2. In the same way, we have shown that we can permit them. So if you permit them, we can take this as this, and it belongs to M1. And then when we add this, it belongs to M1. So what motivates us here to study Beidleman near vector space? In the literature, there have been several definitions of near vector space. The first one is by Beidleman. The second is by Andre. This is another notion of near vector space, but it had been investigated in the literature, while the first has not been investigated. So we're wondering why the first have not been investigated. So in the second one, they derive all the subspace of finite dimensional near vector space. So we want to see what will look like the subspace of all finite dimensional Beidleman near vector space. So what we call Beidleman near vector space is that if we take a nearing module, we can write the nearing module as the direct sum of submodule which has no proper R-subgroup. That is the definition. So an example is every MR which is irreducible is Beidleman near vector space. So in the same way, we can define what we call spanning set, basis. If you define vector space, the trivial question is, do you have a basis? Okay, so we define spanning set, a linear combination, and all those. So if M is a near vector space with the definition of basis, then it has a basis. Why? So if we suppose that M is a Beidleman near vector space, then it can be written as the direct sum of Mi. And Mi has no proper R-subgroup. So if we suppose that Mi is non-zero, is non-null, then Mi can be written exactly as MIR because it has no proper R-subgroup. And this MR is an R-subgroup. So this is equal to the direct sum of MIR. Therefore, the basis is the set of Mi. So it has a basis. And also, we can define the notion of dimension. Now, this is where our work started. So now we want to derive all the finite dimensional near vector space. And since we already proved that it has a basis, and if it is finite dimensional, then we start from 1 up to n. And then we can define a map phi from Rn to M. For every tuple R1 up to Rn, we associate sum of Mi Ri. So we can show that this map is isomorphism. So then all Beidleman near vector space can be isomorphic to Rn. So now we want to classify all the subspace. So to classify all the subspace, we first need to classify all the R-subgroups first. Later, now we classify all the subspace. And we know from the definition of span is a smallest subspace containing a given set. In the same way, we define what we call the gen, which is the smallest R-subgroup containing V1 up to Vk. Now, since we define this, our investigation is to characterize what is gen of V1 up to Vk. What is it? How can we characterize it? So to characterize that, we start to define some set of linear combination. We define what we call LC0 of V1 up to Vk to be the initial set if we start with some specific set of vector. And then LC1 is the linear combination of vector in LC0. LCn plus 1 is the linear combination of vector in LCn. So we define this as a sequence, increasing sequence. So now the first result is that the gen can be presented as the union of increase of all the linear combination. To prove that, we first need to show that it is a subgroup. To show that it is a subgroup, we have to show two properties. As I defined earlier, if I have an R group, an nearing module, we say that it is a subgroup if R under addition is a subgroup. And we have R is a subset of R. So we need to show those two things. So for the first one, we can take two elements in the union. Let's take X and Y belong to the union of Li. So if we have two cases, first, the two belong to LC, there exists some n such that x, y belong to LCN. So for the first case, x, y belong to LCN. Then if we take x minus y, it will belong to LCN plus 1 because it is a linear combination, right? So then s minus y belong to the union already. So the second case is when x belong to LCK and y belong to LCN such that k is less than n. When we take the difference, is belong to LCN plus 1. So it belongs to the union. So we prove that it is a subgroup. So we need to show this. If we take the union and then we multiply by scalar, the question is, will it be also a subset of the union? So by definition, if we take x to belong to the union, it means that S can be presented as sum of omega lambda omega, such that omega belongs to LCN. So if we multiply by a scalar, it belongs to LCN plus 1. And then it is also in the union. So that we need to show that it is the smallest, because Gen is the smallest R group containing V1 up to Vk. So we will define X. Let's define X, which is an R group containing V1 up to Vk. Now we need to show that the union of LCI is a subset of X. So we can prove that by induction, which means that there exists some n such that LCN is a subset of X. If we take 0, we know that LC0 contains V1 up to Vk, which is also already a subset of X. So we assume that LCN is a subset of this, and then we want to show if LCN plus 1 is also a subset of X. So if we take an element in LCN plus 1, it can be presented as this. But we assume that X is an R subgroup containing V1 to Vk. So if we multiply and then we do the summation, it will still be in the group. So this element here belong to X if we do the summation. Therefore, it is an R subgroup, which is the smallest. So another result is that when we permit all the vector, the gen is unchanged. If we permit the vector is unchanged, like we have in for spanning set. If we multiply V by a scalar, the gen is unchanged. So the idea is that we want to check the property for span. If it is work here and see what we can do. So for this, we can show by defining the gen of V1 up to Vk to be the union of LCI, and then gen of V1 lambda up to Vk to be the union LCI prime. And then we want to show the equality. So to show the equality, we can show the first inclusion, the second inclusion. So for the first inclusion, if we take an element in LCI, we can represent V1. In all the expression, we can write V1 as V1 multiplied by lambda times lambda minus 1. Because we suppose that this lambda is not different of 0, so it has an inverse. So therefore, if we do this, we can see that V1 can always be represented like this. In the same way for the other inclusion, if you have V1 is equal to V1 lambda, it can be written as, or maybe multiplied by alpha 1. It can be written as V1 alpha 1. That's how we see the second inclusion. And the same way, we can also show that if you add some linear combination of vector to one vector, the gen is always unchanged. It's the same thing. The same thing also, if we take W, which is in the gen of V1 to Vk, when we add an extra vector, the gen is unchanged. Now, this is the main result that we want to prove for today. So now we start with a vector. V1 up to Vk. We arrange all those vectors in a specific matrix. V1 up to Vk, we arrange all those vectors in a matrix. So we want to generate what is the R-subgroup of those vectors by some explicit procedure. And first of all, we need to get the reduced row echelon form of that matrix. That's the first step we need to do. And when we get the reduced row echelon form of this matrix, what do we get? We get a new matrix that we call W. We all know what is a reduced row echelon form of a matrix. So we get a new matrix that we call W after taking the reduced row echelon form of the initial matrix. So then our new matrix we call W, which is as follows, which contain some row W1, W2 up to WT, we suppose. And then let's see W1 up to WT. So the first case is that if we suppose that at every column of this new matrix, we have only one non-zero entry, then this equality will hold. This one, for the first case. If the reduced row echelon form have only one non-zero entry, this will always hold. But the second case is, we suppose now that for the first GN column, let's suppose we have the GN column here, we have two non-zero entry at the row WR and WX. So we have maybe WRJ, WSJ here. So we have already two non-zero entry at the GM column. So now we're going to find a procedure in order to eliminate this column, in order to find one non-zero entry at every column. That's the idea. So to do that, we need to first assume that this condition should hold. That means that we are working in a proper near field, which is not a field. If it is a field, then this condition should hold. So we assume that this does not hold. Okay? Now, we want to create a new row. We want to create a new row from those two rows, WI and WX. So how can we create this new row? This is the construction. Yes, such that alpha prime is this and beta prime is it. This is how we construct it. And we see that this new row is in LC2 of omega S, omega R, omega S, because we are taking the linear combination of linear combination. And as initial, we show that the gen of V1 up to Vk is also equal to the gen of W1 up to WT, because of the first lemma that I show. If we swap, if we add a new row, if we multiply by scalar, the gen remain unchanged. So as we are doing the retribution form, those are the operations that we did. So the gen will remain unchanged. So now, since we create a new row, we want to be able to create one out of this new row at the column J. That's what we want. And then we need to multiply by a certain scalar in order to get one. So for this new row, theta that we're creating, all the entry at the left-hand side of WR and WX, we either have WR or WX. So we see that theta J here will be always 0. If J is less than, maybe I write L here, if L is less than J. But then at the entry J, we can compute what is theta J. And theta J gives us exactly this quantity, which is non-zero. Now, as we want to find phi, we multiply this new row by this entry, the inverse of this entry. And this will give us a row phi. This phi contains 0 up to 0. Now, at this entry, we have 1. At the GM entry, we have 1. And then we have some non-zero entry here. The new row that we create. So this phi belongs to the gen of W1 up to WT. So therefore, gen is equality. We can write this as the gen of phi. We add this phi with W1 up to WT. And the gen remain unchanged. Now we want to eliminate the row WR and WX from the new row phi. So how we eliminate that? We take a new row YR, this one. This is the new row that we take, and the new row YS. So we exchange the row WR with YR, we exchange the row WS with YS, and the gen remain unchanged. So therefore, we get something like this gen, which is equal to this, is equal to this, but now instead of WS, we have YR. And instead of WX, we have YX and omega T. That's what we get. So we repeat this procedure. Suppose that if you have a matrix and then we add the J plus 2 plus 3, we have also other entry that you have 2 more entry at every column. We can do the same procedure until we eliminate all the 2-0 entry at every column. And this will give us this final result that the gen can be always presented as this, such that the final matrix that we are getting in the column of every the column, we should have only one non-zero entry for this final matrix. I'm give you example to see. 5 minutes, okay. Thank you. So let's do for this example. So we want to, this algorithm that I'm describing, this procedure, we call it EGE, expanded Gaussian elimination, right? Gaussian elimination is making some operation. Since we are working on a near field, we extend it. So we start with a vector V1, 1, 0, 1 in R3. We are working in R3. And V2, 0, 1, 0. So this, no, 1. So our initial matrix is this one. This is our initial matrix. Now we see that at this column we have 2 non-zero entry. So what we're going to do is that we're going to create a new row out of those 2 rows that I will denote as theta. So this theta here, we suppose that we have alpha, beta, lambda, such that alpha plus beta, lambda is different of alpha, lambda plus beta, lambda. Okay, so this theta here is V1 alpha 1 alpha plus V2 beta lambda minus V1 alpha lambda minus V2 beta lambda. So this is how we construct a new row. And with the computation of this, we can see that theta at the colon 3 will give us alpha plus beta lambda minus alpha lambda minus beta lambda with this construction. Okay, so now we can now find the row phi out of this. So we just multiply theta 3 inverse by the row theta. So we get 0, 0, 1. So now we create a new row out of those two rows, and then by the procedure of the lemma that I state, the gen of V1, V2 is equal to the gen of V1, V2, and theta phi. Because this phi here belongs to the gen of V1, V2. Now we're gonna exchange V1 from phi and V2 from phi. So we define maybe Y1 by V1 minus phi, for instance. And Y2, we replace it by V2 minus phi. So then at the end, we get the gen of Y1, Y2, and phi. And this Y1 here is a row which contains 1, 0, 0. Y2 is 0, 1, 0. And then the phi here is 0, 0, 1. So finally, we get that this gen of V1, V2 is equal to R3. That's the result. Okay, so this is a bit surprising because in the vector space, if you take two vectors, when you take the span, you cannot get a yes, and then we have a less vector that gives us a higher dimension. Okay, I think I will stop there. Yeah, thank you. So, question? Maybe I see something that was not clear. I can go through. Yes, thank you.
Thank you, Chan. Interesting topic and very new. You defined the subnearing module. That's the name, right?
Yes.
So I have a question. You know, in a group theory, you can define like a subgroup, and there's a property between subgroup and group. Is it possible to define like subnearing seal or subnearing or subnear seal? Yeah.
Okay.
I just wanted to answer my question. I was wondering if there is a near idea or something. Near idea, because when you talk about a ring, you consider also sometimes ideals. Ideals.
Yeah.
Like normal subgroups.
Normal.
Like in groups, we have normal subgroups because the quotient without mentioning actually what is
Oh, okay. For the nearing module, right? Okay, okay.
For the nearing.
For the nearing, yes. Okay. So the first question is that if we can define a sub module, right? A sub nearing. Yes, 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 sub nearing. So yes. So first of all, we define the structure, right? As a nearing, which satisfies the condition. Okay. So a sub nearing is the same definition as a subring. As a subring, if you take a ring then a definition of a subring is the same as taking a near ring and we define a sub-near ring. It's the same definition. The same. But they have some work in that area. For instance, what is one of the basic results in sub-near ring that you know? If I give an example for field, if you take a finite near field, a subfield, there exists, if I take a finite field of order p to power n, for instance, there exists a subfield of order p to power k, where k divided n for field theory, right? But for near field theory, it works as well. It works. So for a finite Dixon near field of order q to power n, there exists always a subfield of order p to power k where k divided n. But the proof is not similar. It's just we try to generalize it. Okay. So yeah. Yes. So the classification here, this is the classification. Yes. So the classification of all finite near field is classified by finite Dixon near field. So if you want to classify all the finite near field, we first need to derive the finite Dixon near field. So there is a result that says that all finite near field are finite Dixon near field except 7 exceptions. The 7 exceptions are of order 5 square, 7 square, 11 square, 17 square, and so on. So we have only 7 exceptions. So to classify the finite Dixon near field, how do we classify that? We take a finite field. We start with finite field of order q to power n, but we assume that Qn is a Dixon pair, and a finite field is cyclic. It's generated by a certain j. So we can construct a subgroup which is generated by Gn. That's the first step. Then we change the multiplication to become a new multiplication. So those are the few steps. The first, we take Dixon pair, Qn. And then we take the Galois field of order q to power n. We change the multiplication, the usual multiplication that we use for Galois field to become a new multiplication. So how do we define this new multiplication? Here. This is how we define the new multiplication. Yeah. From this coset representation. And then it forms a Dixon near field with a specific generator. So here I need to add that this Dixon near field here is from a specific generator. Maybe I will write a superscript J because of the finite field that's generated by G. Okay, so that is how we classify all the finite Dixon near field. Yeah. No, the N and Q are called Dixon pair. So if you want to classify all the finite near field, all the finite near field, first are finite Dixon near field. So for Dixon near field, you start with pair. Yes, yes. Can you repeat it? Yes. Yes. 7 exception. Yeah. Yes, all the near field can be represented as a Dixon near field, all of them, but except 7 exception. Yeah, and those 7 exceptions are of order 5 square, 11 square, and so on. Those are 7. But apart of that, all of them. Yes. Yes. Yeah. Can you remind me again? Yeah. Ideal for rain, near rain. Yes. There are some, a notion of ideal and radical ideal in near rain. Yeah.
Do you know how to define?
Yeah. Yeah, another question. For ideal? So, okay. So the idea maybe here in our context here, it coincide with the R-subgroup I was talking about here. If you take a nearing module. So for the nearing module, we have that the additive group. Okay, let's consider M to be a nearing module over a nearing. Okay, if I take a subgroup of these, A, which is a subgroup of MR, and I have the extra condition is a subset of R. So this is kind of definition of ideal, right? Right? Yes. So is a similar thing, but just like here, we just make some difference because of the right distributive law that does not hold in that case. So that's why we're gonna derive what we call R subgroup and then submodule. So this submodule here is taking in consideration the distributive law that was omitted. Yes.
So is there a point to be thinking about polynomials with coefficients which are from like...
Yes. There's what we call polynomial nearing. Yes, polynomial nearing. Yeah, where all the coefficients are from nearing. Yeah. I think it has been proved that if you take a polynomial ring under the addition and then the normal multiplication of polynomial, it forms also a nearing. Yes, it's an example of a nearing. Yeah. Yes.
So I just want to check on something. When you were proving some part of theorem number 6.
Theorem number 6. Okay.
Yeah, you just took x and y at the same.
Wait. Let me come back to theorem number 6. This one.
Yeah,
okay.
You take x and y at the same LCM.
Yes.
If there is like x and y, they are different ones. You just have to perform like more linear combination to reach the same one, and then again perform one more to show that they are related, right?
Mm-hmm.
I mean, you have to consider that they can be in different sets or linear things, right?
Mm-hmm. So the question is?
The question is, you just took the case when x and y are in the same LCM.
Yes.
We can have like x in LCM and y in LCM.
Yes.
So we have to perform more linear combinations to make them at the same LCM.
No, okay. So let's see. So if you take 2 elements, let's take 2 elements, x, y, belong to the LCM. I, right? So, okay.
Yes, if they are in the union, they could be in different sets.
Yes. So,
so we have just to cover this case. This is what I'm checking on.
Yes,
right?
yes. The first case is that X, Y are in LCN, right? And the second is X belong to LCK, Y, LCN. Those are the two cases.
Yeah. Thank you.
Okay, good.
So I'm more interested in any counting related question.
Okay, good.
Are there some
Combinatory.
combinatory questions?
There is a combinatory question
arise
here.
from your work, and number theory question as well. For instance, is there results about counting all those distant pair when we give the upper bound on Q, for instance? How many are there? At least asymptotically speaking. Do you have some result like that? Or?
I think a good question like that we already discussed it
Okay.
sometime before is in the very end you were saying you have this that you have like a set of k vectors.
Yes.
The dimension of what you generate can be greater than k.
Yes.
Which is like not at all. So you're like, what is the best possible upper bound of this, for example?
Yes.
Start with k vector.
Yes. So
maybe those xi might become stable from some point onward.
So
maybe LC1, LC2, LC3. Of course, the union of finite. I mean, a countable set, but then maybe from some point onward, we may end up with some big M or something like that. Not necessarily goes to infinity or something. Have we tried to see for some special set of vectors, we may not go to infinity or
okay.
At least when it's finite, I know that we cannot go to infinity. I mean, from some point onward, we just have equality between LCI.
Okay, if I take this example, the example that I was doing here, we take this vector v1 up to v1, v2. Okay, so we want to generate chain of v1 and v2, right? And if we compute the linear combination, here we see that at 2 we have already the whole space.
And that's a very nice question. I mean, research question. I mean,
but in general case, we don't know at which level we get when we are taking the union. Yeah. Yes, that is one combinatory question. And other one is to find maybe as a future work to find the smallest set of vector that will generate the whole space.
Rn.
Yeah, Rn. And that could be expressed as the size of R, the finite near field with the dimension n and something like that. So first we find out that we have two that generate the whole space with a specific condition.
Okay. Yeah, you want to relax this condition.
Yeah, with a specific condition. If we know that the n is less than, if n is less than the size of R plus 1, then we can construct two vector v1, 0, 1, 1, 1, 1, and we can construct another vector v2, 1, 0, maybe some vector, some non-zero entry, w1 up to w maybe t. And those w here will be from the finite near field. So which means that each tuple here will be distinct. Like 1, w1 must be different of 1, or maybe a scalar multiplied by 1, w2. So when we compute the EGE algorithm on those two vectors, we found out that it will generate the space Rn with two vectors. Yeah. Example, for this, if we take 2, we can find Rn, R9. The chain of V1, V2 can give us a space of dimension 9. If we consider a finite Dixon near field that we say earlier, that derive from the Dixon pair 3, 2. This one. If we consider a near field as a finite Dixon near field, we find that chain of V1, V2 generate Rn, R9. But in more general sense, we don't know yet. Yeah. Other question?
Okay, thank you. Yeah,
Thank
I
you.
think it's almost 4 p.m., so it's a good time to stop.
Yeah, thank you.
Thank you very much for this.
Yeah.
Also, I want to thank for active participation. We actually spent a lot of time on the questions. Yeah, that concludes it for today. Now it's time for the coffee break, and we'll meet tomorrow at 10:30.